Okay, so what exactly is light? We talk about light, and what do we mean when we say light? Are we talking about visible light? Okay, visible light is a form of light, but sometimes we talk about ultraviolet light. Is that light as well? We also occasionally talk about infrared light. Okay, and the point of this is that we're really just talking about an entire spectrum of different types of radiant energy, and the spectrum is known as the electromagnetic spectrum, sometimes called the EM spectrum, electromagnetic. And what it is it is a continuum of radiant energy. So visible light is part of it, ultraviolet light is part of it, and many other frequencies and wavelengths are part of it. And this diagram here shows the basic categories. Visible I've put in the middle, and that's what our eye sees. To a higher energy, there's ultraviolet radiation. Higher than that is X-rays, and still higher is gamma rays. On the lower energy side of the spectrum is infrared light. Lower than that is microwave, and we usually don't use the term light once we get past infrared, but it's all radiation, and then finally radio frequency. And so on the way I've drawn this here, the wavelength is increasing as you go to the right, and the frequency, which you remember was inversely proportional, gets larger going to the left. And we focus on the visible spectrum often because that's what we can see. And so if you blow up just the visible part, we distinguish different colors because our eye sees color, and we refer to these as Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. So that's where we get Roy G. Biv, only the way I've drawn it here, Roy G. Biv is backwards. You could flip the whole thing around and it would be forward. Alright, and then this entire spectrum is all different wavelengths and different frequencies. Sorry, I had it backwards. Different wavelengths and different frequencies. And so they're different wavelengths and frequencies. But one important thing you need to remember is they all have the same speed. Remember, they all are related by the formula C equals nu times lambda. So they all have the same frequency. As wavelength goes up, frequency goes down, but the speed of light stays the same. So the speed of a radio frequency wave is the same as the speed of a gamma ray. Okay, so the classical way that energy and matter are viewed is that they are very distinct. Energy is one type of thing, matter is a completely different type of thing. And energy, one form of energy, is light. So the light we've been talking about is a form of energy, according to the classical view. And matter is stuff you can hold in your hand. You can't hold light in your hand. Okay, so in the classical view, light is viewed as a wave. Okay, we've talked about waves. And matter is viewed as particles, and they are distinct. And this idea explains a lot of things we observe. Okay, we observe diffraction patterns. That's where light bends around a corner, and that is explained well by the idea that energy and light are waves. Interference, which is related to diffraction, is also explained by this view. And refraction. Refraction is how something bends when it hits a different material. So for instance, like light, and we'll show light as a wave. If light hits the surface of water, it tends to bend. Whoops. It tends to bend and I can't do that. And go off at a different angle. Okay. Okay, and that makes sense with it being a wave. If you have particles that are being like a rock being thrown at the surface of water, you don't expect it to suddenly change angle and be straight. You expect it to, oh dear, what have I done? You would expect that it would simply start curving downward, but it wouldn't suddenly change angle. Okay, so that's in water. That's refraction. So all these three things that I named have are explained quite well by the idea that light is a wave, and it's very different than a particle. Here, I'll write this as a rock. Okay, but the classical view doesn't explain everything, okay, and it fails for these three things I'm going to mention. And when it fails, you need a quantum view. Okay, blackbody radiation. That is where you heat something up and it glows. Like when you look in a campfire, the hottest parts of the campfire are glowing. They're giving off light because they are really hot. Okay, an incandescent bulb works the same way. You put a current through a filament, and when it gets hot enough, it glows, and that produces the light. Okay, but that phenomenon, if you try to explain some of its properties mathematically, does not work with the classical view. Okay, so that's like a light bulb. And it's like coals, hot coals in a fire. The photoelectric effect is where you take a surface of metal and you shine light on it, and you can get electrons coming off. That's the photoelectric effect. Put light on it, you get electricity. All right, this also is not well explained. The exact characteristics of how it behaves is not explained by the classical view. You need a quantum view. And in fact, Einstein was the one who came up with the idea that light is actually a series of particles. Light comes in particles. And we now call these particles photons. So a particle of light is a photon. And this equation here gives the energy of a photon, and it's related to the frequency of the light and a constant that we will talk about in a few minutes. All right, and the third thing that's not explained by the classical view is atomic spectra. When you take an atom and excite it with heat or electricity, you will get certain light frequencies. Okay, so atoms emit specific light frequencies. Not all light frequencies, but specific ones. Okay, not all. And they will do that when they are excited by light, by heat or electricity or other things. Okay, and let's see a picture of a spectrum. We're just going to focus on part of this picture. Okay, we're just going to focus on this area. And so this is a view of the spectral lines of the hydrogen atom. So this is atomic spectra. And the wavelength is given on this scale, which is in angstroms, and notice that wavelength is increasing to the right. Frequency is on the bottom scale, and it is increasing to the left, so they are opposite, as you expect. And there are these white lines that you see are the spectral lines. These are places where the hydrogen atom glows, different frequencies and wavelengths. And you'll notice that there's three kind of areas. Okay, there's this area. Okay, we're not doing that. There's this area here that's called Lyman, and it has a certain pattern. And notice that same pattern is very similar to this area, which is the Balmer series. And then you have the third one, which is the Paschen. So we have three different areas where we get light that have a similar pattern. And the Lyman series is in the ultraviolet, and the Balmer series is in the visible region of the light spectrum, and Paschen series is in the infrared. So this was observed. And first, before they understood what the point of it was or what it was representing, they were able to use an equation to explain or to show where all the lines are. So this is the Rydberg equation, which explains the spectral lines of hydrogen in particular. And lambda, again, is the wavelength. So that's the wavelength of one line. And it's given by the Rydberg constant, which we write as R. And this is the Rydberg equation, so it's Rydberg constant, which is actually 1.097 times 10 to the 7th inverse meters. Okay, and then there's these two n values, n1 and n2. And they're each squared, and there's one over them. 1 over each of them squared. Okay, so it's n1 and n2, and those are integers. So all the different spectral lines that we saw above can be calculated, their position can be calculated by putting in different values of n. And the n's, one of the n's is given below here. I wrote it in. So one of the n's is 1 for all of the first group, 2 for all the second group, and 3 for all the third group. And you'll understand what these n's are in a few minutes. Okay, but anyway, they used the lines and they experimentally determined where they were, and then they could use this equation to exactly predict where they would be. And that is the hydrogen spectrum.